Yeah, so today we'll move on to the next lecture. So today we are going to start for two topics, which is normal and exponential random variable. We'll start with the lighter one, which is exponential. Okay, so this is a easier one as compared to your normal. Okay, so we are just going to do a quick review of this. So the function of this is nothing but x e to the power minus lambda x, so lambda e to the power minus lambda x or 0, when this is when x will be greater than 0, and this will be all the other cases, right? So in any case you can just find out the CD like the CDF in this manner. Let's say this is f of some a, right? So f of a is what? P of x less than a. Okay, so whenever you say this thing, it will be nothing but 0 to the power a f of x dx, because the rest of the cases is 0, right? So it does not matter. So it is lambda by lambda, sorry, minus e to the power minus lambda x 0 a. So this comes out to be 1 minus e to the power lambda a. Okay, so in general form you'll try to solve using this equation. Now we have to also check if this is a probability distribution function. If it is a PDF, simple thing, 0 to infinity lambda e to the power minus lambda x dx is what is it? So it will be just this thing only. We'll just put this e to the power minus infinity. So e to the power minus infinity is close to 0, so this becomes 1. So it's a PDF. Okay, so like this. And now we also will try to find out the expectation. So how do we find out the expectation? So instead of finding expectation, we'll try to find the value of this one, e x to the power n. Okay, so it will help us solve this more directly. So e x to the power n can be written as minus infinity 0 to infinity x to the power n lambda e to the power minus lambda x dx. So wait, lambda x dx. Okay, so now we will integrate it by parts, where this is, let's say, your one part and this is another part. So you'll get minus x to the power n e to the power minus lambda x 0 to infinity plus 0 to infinity e to the power minus lambda x n xn minus 1 dx. Okay, so this comes out to be, this is, yeah, this is, I think 1 minus a 0, this is 0. Okay, so this comes out to be n by lambda integration 0 lambda e to the power minus x to the power n minus 1 dx. Okay, so just rearrange that a bit, and now after this what we get, e to the power lambda e x n minus 1, right? So we find out e x to the power n follows this kind of an equation. Okay, so now let's try to find ex. Ex will be, n's value is 0, so it will be just by n by lambda, right? So we have to put the value of n equal to 1 here, so it will become 1 by lambda, and ex square will be nothing but 2 by lambda ex, so 1 by lambda, so this is 2 by lambda square. So variance of x will be 2 by lambda square minus 1 by lambda whole square, right? So this becomes 1 by lambda square. So the expectation is nothing but 1 by lambda, and your variance of x is 1 by lambda square. So these are the equation for exponential. Okay, so this is how you solve for the, and all the questions here are very straightforward, just using the formula. You'll not have something very different or very weird. Yeah, now we come to the most important thing, that is your normal distribution. And how does the normal distribution look? It's called the bell curve or the Gaussian curve. It looks something like this. The basic simple equation of f of x here is nothing but 1 by 2 pi delta e to the power minus x minus mu whole square by 2 delta square. So this is your normal, the function of this. Okay, so you usually get something like a curve like this when it is perfect. Okay, so basically during the case of we represent this as this something like this. Okay, where we say mu delta. Okay, so usually we do some standardization and try to bring it into 0 and 1 like this. I'll go into detail of this in the later thing. Okay, so let's say x is like a random variable and x is normally, we consider this to be normally, and this is called the bell curve. Okay, which is symmetric about mu. And now one very good corollary that comes up from it is the central limit theorem, which we will teach later. Okay, and it's a very interesting thing. This is like the very important. Okay, this is very important, and it comes from the base understanding of how this normal thing happens. So now we are first going to say, how is it a PDF? Is it a PDF? So we need to prove what? We have to integrate it, right? So I'll do integration minus infinity to infinity 1 by root over 2 pi delta square e to the power minus x minus mu whole square by 2 delta square dx equal to 1, right? So do something. Let's take y is equal to x minus mu by delta. Okay, and try to substitute it here. After the substitution, you will see it becomes 1 by 2 pi delta, sorry, no delta, 1 by 2 pi minus infinity to infinity e to the power minus y square by 2 dy. Okay, so what we do is that we take another like I, so let this be I, so we can take another I as 1 by 2 pi root over 2 pi integration minus infinity to infinity e to the power minus x square by 2 dx. We can change the variables, right? So now what we will do, we will take I square. I square is what? Integration minus infinity to infinity. Let's not consider this thing here. Okay, let's not consider this. So basically we have to prove this integral is root over 2 pi. If I can prove this, then it is good. So I am taking only this part. So I will become e to the power x square plus y square by 2 dx dy minus infinity to infinity minus, it's a double integral. Okay, simple logic. Now convert it into polar coordinates. Okay, so x becomes r cos theta, y becomes r sin theta. Okay, just substitute the values. You will see I square becomes integration 0 to say infinity and 0 to 2 pi e to the power minus r square by 2 r d theta dr. Okay, now we slowly break this down. 2 pi integration 0 to infinity r e to the power minus r square by 2 dr. Now again simplify, it will become 2 pi e to the power minus r square by 2 0 to infinity, and this becomes 2 pi itself. Okay, this will be minus. So and solving this you get minus 1, so it becomes 2 pi itself. So i's value comes out to be root over 2 pi. So the whole thing, see, if it is root over 2 pi, so this becomes root over 2 pi. So your final answer would be root over 2 pi into root over 2 pi, that's 1. So it's a PDF. Okay, it's a PDF. Okay, now how do we find out the expectational variance? Before that, I will talk you about something called standardization. Standardization is something like this. I'll explain. Okay, so for example, if you see this thing, right, so like 1 by root over 2 pi delta integration minus infinity to infinity e to the power minus x minus delta x minus mu by 2 delta square dx. Okay, so like take not y, take z. So here you can see it is something like mu delta, right? What you do now, take z is equal to x minus mu by delta. So dz is equal to nothing but 1 by mu dx, right? And you can possibly substitute here. So this becomes 1 by 2 pi integration minus infinity to infinity e to the power minus z square by 2 dz. So you can say this is nothing but normalized, and normal it becomes this, see, because it is, you can write this as something like z minus 0 whole square by 2 into 1 whole square, right? So this becomes my delta and this becomes my mu. So this whole process is called standardization. I am doing the standard form. Okay, so the earlier thing is called the normal form. Now we are doing standardization. This is standard normal form. Okay, so usually try to bring it into standard normal and solve the sums. So we'll also start by finding the expectation and variance now. So the expectation e of x. Okay, e of x. So how do we find e of x? E of x is nothing but integration minus infinity to infinity x f of x dx, right? So we can write it as 1 by 2 pi integration minus infinity to infinity x e to the power minus x square by 2 dx. We are taking all standard normal. Okay, right now standard normal. Okay, so 1 by 2 pi, so this becomes 1 by minus 1 by 2 pi e to the power minus x square by 2 minus infinity to infinity. This is, the value of this is 0, so this comes out to be 0. Okay, so the expectation here is 0, and the variance, you have to find by ex square. Ex square is what? Integration x square e to the power minus x square by 2 dx 1 by root over 2 pi minus infinity to infinity. Do by parts. So what is it? 1 by 2 pi minus x e to the power minus x square minus infinity to infinity plus minus infinity to infinity e to the power minus x square by 2 dx, right? So this is 0, so this comes out to be 0, and you calculated this earlier on. This is root over 2 pi, so the variance comes out to be 1. So the e and variance is 1 and 0, so it is very similar to the mu and delta. Okay, so basically x is this. Okay, so now what we do is that, see this equation, so we can write this as like, I am not telling this is the correct answer and this is like an empirical form. So let me try to show you something. So like, so x minus mu by delta is equal to z, right? So x's values is mu plus delta z. So ex will be equal to mu plus delta ez. So ez is 0, so this is 0, so mu. See, so the expectation of that variable is mu. Now the variance. So variance of x will be nothing but mu variance, I think, yeah. So variance AB, sorry, AX plus B comes out to be A square variance of X. Okay, so the B terms get cancelled, so no mu. So it will be this into variance of Z. So that is 1. So it will be mu square. So this is how I found out the expectation and variance for a normal equation. Okay, normal random variable. Now we are going to talk about something in very detail, 2-3 sums and how to solve them basically. Okay, so let's try to solve this kind of sums. We'll do one sum, two theory. The length of the bolts produced by a machine are normally distributed. So let's try to write the details as we go on. Mean is 4, SD is 5, does not lie here in this range, find the percent of, and these are your hints. Okay, not hints, like useful stuff, right? So basically that is given. So first, every summer like this, try to normalize it. Okay, so not normalize it, as in like standardize it, sorry. So Z becomes X minus 4 by 0.5, right? So what are the limits, right? So limits are 3.8. So for 3.8 it will give you 3.8 minus 0.2 by 0.5, that is minus 0.4, and 4.3 is your 0.3 by 0.5, that is 0.6. See, these things are coming here right now. These things are coming useful. So these things, I'm going in the correct direction, right? So yeah, so let's move on now. So now what is the probability of percentage of defective bolts? Okay, so if it is defective, if it is not in this interval, right? So basically I think we should solve it like this. So let's find the probability in that range. So P of 3.8 X 4.3. So that comes out to be P of minus 0.4 Z 0.6, right? Okay, so let's draw the graph like this. Okay, let's imagine the graph. So we are talking about, let's say, this area. So can we do this? We'll take this whole area minus this area. So it will be something like 0.6 minus 0.4. Okay. Okay, so by this I mean the normal form. Okay, so this is 1 by root over 2 pi integration e to the power minus x square by 2 dx. Okay, so let's find this area. So this minus 0.4 is basically what? Probability of z less than equal to minus 0.4, or we can say it is P z greater than equal to 0.4, because if this area is symmetric to this area, right? So normal curve is always symmetric. So if I am taking this area, I can also take this area. It's the same thing. So I can rewrite this as it's given how much? This is so this is given minus yeah. So see the second integral. Second integral is given from 0.4 to minus infinity, means this area, but we need this area. So 1 minus 0.6554 should be our answer, right? So this value is 1 minus 0.6554, that is your 0.3446, and this value is actually given. Yeah, this value is actually just bluntly given. So this is 0.6554, 0.7257 minus this, so this comes out to be 0.3811. So non-defective bolts are this is non-defective, so defective would be 61.89, right? I don't know maths, man. Yeah, 69% are the defective bolts. Okay, so this is how you solve these kinds of sums. So this is a very common sum. These kinds of sum will be coming a lot, so know how to solve these sums. So you saw using these two values I was manipulating using the graph, so always think around the graph and try to solve using the graph. Okay, so that should be your goal. Now a pretty useful kind of equation you will need to know is that when we have x that is tends to the Gaussian curve of np root over np 1 minus p, and z is equal to x minus np by root over np 1 minus p, we can say a Bernoulli, actually binomial, it becomes a Gaussian. So Gaussian is basically a normal thing, so basically a binomial curve becomes a Gaussian curve. Okay, so whenever you have, like, let's say coin toss and you want to convert it to, let's say, a normal form, right? It mentions use like normal approximation and everything, right? That no, so what you find out is that you find out the mu is what? Np, and variance is your what? Np into 1 minus p. Then use z x minus mu by delta, input the values here. If you see, this value is basically this z value, and make it into a normal curve. Okay, and then solve it like that. So that is the method of solving you should have when you are given such questions like binomial questions like coin toss. Then you have to solve it using normal and everything, right? Then that is the approach that you should do. And now finally a question that would be like an open-ended question, I will not solve this, is that for any normal distribution, okay, normal distribution, the mean deviation, that is your like average deviation, actually average deviation from mean is equal to 4 by 5 into your standard deviation. This is a very important formula, can help you solve sums very easily, and this is your prove this. Okay, this is actually a like not a hard sum, just a huge calculation sum, so you have to try to prove this. So with this we finish normal distribution as well, and next day we will go to t distribution, chi-square distribution, etc.